It's our pleasure to have Jeannette Bohg give the first talk. So she's an assistant professor at Stanford University, and her research focuses on perception and learning for autonomous robot manipulation and grasping, and she's interested in developing methods that are goal-directed, real-time, and multimodal, such that they can provide meaningful feedback for execution and learning. And she's received a number of awards, most notably the 2019 IEEE Robotics and Automation Society Early Career Award and the 2020 Robotics Science and Systems Early Career Award. So yeah, we look forward to her talk.
Thank you. Thank you so much to the organizers, and thank you for the nice introduction, Daniel. Okay, so today I was thinking about talking some of our most recent works, and in that context, I want to maybe pose the question how we actually should represent deformable objects. Should they be represented in an object-centric way or not? I'm going to explain this in a second, what I mean by this. Yeah, let's see what we've done over the years. And actually, I have to say, in our work that we have done, of which you see some samples here, where we actually have robots manipulate deformable objects, we've used kind of a hodgepodge of ways to represent deformables, really. These are all the different works. You can see the references here. I'm not going to go into details of what these works do. I'm actually going to talk in detail about a different work. But let's just look at what representation they used, right? So here we have the first one that actually is a diffusion policy-based work. There are lots of details, but essentially it uses an RGB image, the entire one, to represent the entire scene, including, of course, the deformable objects, or, on the bottom there's like a bunch of trash that is being swept, which I counted here as deformable object as well. Then we have some other work that is called Equibot. There we actually use a more object-centric approach, what I would call object-centric, because it does use SAM to actually segment this comforter on the bed, and then uses the point cloud from this comforter to actually use that as input to a policy, which then steers these two robots to cover the bed. This work down here is TidyBot, that actually has top-down ceiling cameras in this case, and looks at the scene from the top, and just uses a segmented top-down image, segmented through object detection, basically to detect where these objects are. And then the grasping, the pick and place action here is actually super simple. It just basically grasps the center of this blob that happens to be a deformable object, and then sorts it based on the properties into these different receptacles. Here we have another work, completely different, it's called RoboFume, where we do learn like a multitask policy and actually have it learn to do other new tasks as well. And there we had also some deformable tasks. That one also uses the entire RGB image as well, right? And here we basically use SAM and a point cloud for this collaborative manipulation task. And so, yeah, so again, I don't talk about the details of this work. I just want to show you, it's like, I don't think there is an agreement about how to best represent deformables in the real world as input to our policies or controllers that we're using. But I also want to mention that for these different works, you see like most of the actions that are done here, except for maybe to the very left, are very much variations of pick and place, right? Like it's usually a simple picking of deformables. It doesn't matter where you pick up the deformables, you just want to place them somewhere in particular. And so I think that maybe if we have other tasks that are more complex that actually want to use this deformable in a more semantic way, like let's say you want to hang this tote bag on the hook, or you want to dress someone, help someone actually dressing, or you want to pack a grocery bag or maybe unpack a grocery bag, or you want to put clothes on a hanger, that's where you actually need a more detailed understanding of what the objects actually are and understand maybe their parts. To like manipulate them in the goal-directed way for the particular task you are interested in. And so today, and for these types of tasks, I think we need a more object-centric representation. And I also think that actually point clouds are really useful for that, because you do get a geometric understanding of these of these objects to maybe do a better semantic understanding or feed into a better semantic understanding of them. And again, I don't have the answer, but I'm just going to show you a method that we worked on very recently. And so in particular, I want to talk about a method that uses both topological and geometric representations to represent a deformable point cloud and actually do semantic part segmentation for these highly deformable parts. Let's talk about what actually is going on in that space, of which many of you are probably familiar with, right? So first of all, there's a lot of point cloud processing methods. There's PointNet and PointNet++, very familiar with those, right? There's also DGCNN, which actually uses graph convolution to represent point clouds. And these are all considered geometric deep learning methods because they exploit local geometric structure with simple methods like KNN or a ball query, actually. So these are very purely geometric methods. And the question is, how could these be made work for deformable objects, or do they work for deformable objects that actually undergo these continuous non-rigid transformation that disrupt the local Euclidean relationship that is actually static for rigid objects, right? And so let's just look at an example. So this is a tote bag. It's a very common deformable object. Probably some of you have it right now in their hands. And let's say there's a robot that wants to put stuff into this tote bag, right? And so when we see a picture, or when we see these picture of the tote bag, so the semantic part segmentation that you might need to do for, or that a robot might need to do to maybe put groceries in this tote bag appears kind of straightforward, right? Like, because the handles are there and the body of the bag is kind of easy to detect, right? So I just kind of outlined it here. And that would help for the robot to know where to grasp and to hold the tote bag and manipulate these handles, maybe to find the opening of the bag and open it further up. Okay, so so the traditional point cloud processing method, like PointNet or PointNet++ and so on, they would rely on geometric relations that were captured with KNN or a ball query, like I visualized here, right? So for example, you place this ball query at that point on the back handle and kind of looks like this. So this basically all the points within this neighborhood are basically taken into account to compute like local features. And now let's look, let's look at other states, configurations in which this tote bag shows up in the real world, right? Like here, just a few pictures of how this tote bag looks like. And so here, semantic part segmentation is maybe not as straightforward anymore, because if you look at where the body and where the handles actually appear, they are often like overlapping with each other, right? So the handle part is very close to the body. And so if you just do a simple ball query, like with those traditional or these prior methods, right, like you suddenly have in this neighborhood also points of the handle and of the body as well. And so it makes it just harder to use this local geometry to really do the semantic part segmentation as well. And so so basically, but what you also see is that, of course, the parts are still the same. They're still connected in the same way. The body and handles, like this whole global connectivity structure is still there. And so that is invariant, even under these crazy deformations that deformables are undergoing. So what we propose to handle this and to capture invariant global structure despite these changes in Euclidean geometry is to use topology-driven methods. And we hypothesized that because topological data analysis aims to capture the connectivity structure of data, and the connectivity remains invariant to deformation, this should improve the semantic part segmentation, okay? All right, so that's our hypothesis, and that's a method we're going to develop. We're basically going to take the prior of topology and embed them into a network. And if you've been at the debate yesterday, there was this nice fight, priors or no priors, data versus priors, right? Like, so this work squarely lives in use the priors to basically regularize this whole problem of part segmentation, right? Okay, so So that's great. So, but now, how do we test this hypothesis, right? Like of actually incorporating priors into these networks and whether this actually helps. And for that, we actually need some kind of data. And it turns out the available data sets for point cloud processing and especially semantic part segmentation are mostly in rigid, and some of them are in articulated objects as well, but there are none for deformables. And so that's one of the contributions of this work that I hope is really interesting to you all in this community. It's this new data set. It's called Fabric Deform 3D. And it has basically more than 37,000 annotated point clouds from 15 different deformable object classes. And it has 65 different semantic parts. And yeah, so there are, of course, also different unique instances for each class, or you could think of them as styles of bags and dresses and skirts and so on. And also, we don't just have like static objects here, but they are actually being animated. So this is actually the different types of trajectories that are generated for these object classes. And so, for example, there's this action of draping stuff over a chair or some kind of clothes thing. I don't know how these things are called. Or like dressing someone, right? Like this vest in the middle is actually wrapped around an avatar that you don't see here. It's not shown here. Or you are hanging this tote bag on a hook, for example, right? Like, so these are all the kinds of trajectories that these object classes are undergoing, and we inject random noise and vary camera viewpoints to have a diversity in these trajectories as well. So where does this come from? So it comes from this DIDO work that was published by Rika Antonova et al. A few years back. And so we use that to actually generate these trajectories. And then we also use open source mesh repositories to actually get these deformable objects and just these meshes. And now the big challenge is actually, how do you label these parts of a deformable object, right? Like this could be like super annoying. So let me tell you how we did that. So here's the data labeling procedure that happens in 2 steps. We are, first of all, the first thing to know is that we are not directly labeling the point clouds because that would be truly annoying. So we instead created this interactive display shown on the left where we would select the vertices from the mesh, actually, not from the point cloud, for each semantic part. So on the left, you see that we selected all the vertices related to the skirt waist, and that is shown in green. And after doing this for each semantic part label, you can see on the right that we have the completed vertex labels with the waist in red, the body in blue, and the bottom opening in green as well, right? Like, so again, this is not the point cloud. These are the vertices of the mesh, okay? All right, and so then basically we run this trajectory of the skirt in the simulator that is basically based on Pybolid. And acquire the point clouds by basically rendering the skirt from 4 different depth cameras. And then we have a point cloud. And how do we label now the point cloud finally? We find the nearest mesh vertex to each point cloud point per time step. And we get the following labeled basically point cloud that you see there on the right. And this point cloud is shown in this canonical non-deformed state, right? Like, so in the database, of course, there are like much more crazy deformations basically of the skirt, but this is kind of how it looks like completely unfolded. Okay, so so the benefit of directly labeling meshes is that it's easier to find the correspondences between the point cloud points and the labeled mesh vertices than to hand label the deformed point cloud. So it's much easier to scale up actually data labeling, but it's still quite challenging. Because many of these meshes, like the one that you see here, have very uneven vertex and triangle distributions. And in this example, we show this mesh of a skirt, which actually was ultimately discarded because the triangles are much more fine-grained at the waist, but then they become really sparse at the bottom. And so that is a problem, right? Like when you're actually labeling the point cloud, it kind of looks weird. So basically, we discarded meshes like this that had kind of not a very nice regular uniform triangle distribution as a mesh as well. Yeah, so these were the details on how we basically generated the fabric deformed 3D data set that I really hope we're going to release it soon. So I really hope it's going to be useful for you for doing research as well. And so now we have our data that we can actually use to evaluate whether our hypothesis of embedding topological methods into a network structure actually is useful or not. So let's look at this. So we, in this paper, also propose a new point cloud processing architecture for these kind of for this problem of part segmentation, and we call this topometric graph neural network, or TOM-GNN. And here's just the input and the output for this network. So actually, we take not a single point cloud as input, but two consecutive point clouds to also exploit temporal information as well. And then, so you have like in the middle this kind of not black box, but pink box of this method that I'm going to show you bit by bit. And then at the output of this network basically feeds into a simple MLP that then finally does the semantic part segmentation for both of the time steps as well. Okay. So what this method really does, it aims to fuse topological and geometric information to improve this part segmentation. So how do we get to this topology, right? Like, how does that work? So we use a tool from topological data analysis that is called the mapper algorithm. And I want to explain to you this. So basically, what that does, it captures global connectivity structure, or it captures connectivity structure in the form of a graph of a point of actually any kind of data that has been applied to many different kinds of data problems. Like, for example, analyzing NBA players and their gameplay and things like that are really not, let's say, explicitly geometric, actually, but here we use it for point cloud processing. So let me just give you a brief overview of how this mapper algorithm works on a very simple 2D toy example, okay? So here is the following point cloud as input data. It's just a circle, as you as humans can see. And so now let's first select a filter function. So this is something you as the engineer actually selects. That in this case, for this toy example, projects the data along the y-axis, okay? That's the filter, what is called the filter function. And then we create a cover that in this case is composed of 3 overlapping intervals, and it's applied to this projected data. And then we cluster within each of these intervals, so with each of these parts of the cover that actually separates points from each other. And then this ultimately forms a cyclical complex, or you can think of it as a graph as well, where nodes represent clusters and edges connect the overlapping regions between the covers. And here is how the actual final output we are interested in looks like, what we call the TOM graph. So basically, we use a geometric interpretation of this topological structure to merge topology and geometry. So this is what we call this TOM graph. It's a spatial TOM graph because it's not yet taking temporal information into account. It operates per time step. And so the TOM graph introduces edges within clusters. So you see like all the points within one cluster are actually connected, densely connected to each other. But it then also enforces the connection that comes from the cyclical complex, right? Because points that are in the overlapping regions are connected to the points in both of the regions as well. And so that's what we finally have. And then how do we use this now in 3D? So basically what we do is we have to pick the filter function. In our case, our data is already a 3D in 3D, right? So we don't have to do a lot to make it geometric. So we actually use the identity there. And maybe there could be other ways on how to do this, but we didn't study this yet. So that could be an interesting question. And then for the covers, we actually use overlapping cubes. So we split the whole point cloud into cubes that are actually slightly overlapping with each other, which is also, the amount of overlap is also a hyperparameter we have to choose. Okay, so that's how we basically get this TOM graph at the bottom, but for 3D data and for this particular point cloud data. And so this is kind of how this looks like. Now now already for the temporal case, but so that you just see how here you see per time step actually how a single cluster in this spatial tom graph actually look like. It's just an example, right? So actually in this paper, what we do, we extend this original mapper algorithm to a sequential mapper algorithm, where we first run this algorithm I just showed you on each point cloud in the sequence to produce a tom graph per sequence. And then each node in the spatial tom graph represents this topological neighborhood that you see here on each of the shoulders, basically, right? And for each time step, we show this topological neighborhood in blue, pink, and yellow. And then we embed the spatial graphs in Euclidean space by taking the centroid of each of these neighborhoods. And then the closest nodes across time become temporal topological neighbors. And this is what we call the spatial temporal tom graph. And the visualization here is basically you have a subset of connections across time between corresponding nodes of consecutive spatial tom graphs. Okay, so that's what we do to create this tom graph over both space and time for our point cloud. Okay, so now you kind of know what's happening in this mapper algorithm. And now let's look how we embed this actually in this architecture. So again, we have as input these two consecutive time steps of a point cloud. And now we do this mapper transform that I just showed you, which produces the spatial tom graph for each point cloud to capture the intrinsic connectivity structure of this point cloud. So that's what we have here. So that's now outputting basically a feature map. And then we have the step called what we call tom fusion, which combines the topological, geometric, and semantic features into one unified representation for each point cloud. So it basically now combines all this information. It ensures that points with semantically similar properties are embedded closer together because they have similar features. And then we use spatial and temporal tom graph attention, shown there kind of in the middle. And this layer derives its attention mass from this spatial temporal tom graph as defined by this adjacency matrices in the tom graphs that I showed you before. Yeah, and then everything is combined through residual connections. And we do this fusion actually 3 times. Again, the 3 outputs are combined with the residual connections. And then we have the simple MLP at the end that produces the final semantic part labels. Okay. So that's the method on a very high level. I hope we have the paper out very soon, and so you can also read up on all the details. And so now let's look at some results, okay? So we compare this method to 3 seminal methods. Obviously, there's PointNet and PointNet++, and we also compare to DGCNN, which is a method that also is very graph-based, but it actually uses KNNs instead of topological neighborhoods internally as well. So actually the methods, you could think of it as roughly, these methods are very similar to one we propose in DGCNN, but one uses topological information, one uses local Euclidean information. And then we also add 2 more baselines of recent methods that are at the top of the ShapeNet part leaderboard. So they have been shown to work really well for rigid objects. Or actually articulated object in this case. But for example, PointNext, for example, requires normals as well. So we added just for this method the normals as well. And you see that actually both of these high-ranking methods on the articulated object data sets are actually not as good as this much older method that is called DGCNN. So DGCNN is really the strongest baseline, and we still outperform it in the end over all of these different classes by 2.1% mean intersection over union. And you see, like in general, we outperform DGCNN by in 10 out of 15 classes, and sometimes it's also still very close. And now we are in robotics, so you think like, oh, but we usually have 40% increase, right? Like, what's this 2.1%? Okay, let me show you where this comes from, actually. So here we have like basically some qualitative results where you see the baseline, the best performing one, DGCNN, with some results, and our method, and then the ground truth. And so one thing that you see first is that both of these methods are working pretty well in like uniform areas, right? But where the difference actually comes from is where these different parts are connected. And that is, of course, super ambiguous, right? Like it's even hard to label that sometimes in the data set. But that's where these 2.1% actually come from, by an improvement actually at these seams that are overall like a much smaller amount of point clouds. So here's some other more qualitative results on this as well. And here we see also, which is maybe a little bit hard to see because I can't stop these in like one frame, but you see a bit, again, this dressing application of basically a robot putting on a vest on a person. And you see here the differences in the semantic part segmentation. Okay, here's another one with the tote bag actually hanging it as well. And yeah, and here you have another one where a shirt is basically draped over some kind of clothes hanger. Okay, so with that, I'm actually already at the end for today. I wanted to show you today this work where the first contribution is really a data set that I hope is like useful for you. We did specifically semantic part segmentation because that's kind of like an established task on all these rigid objects and articulated object data sets. But I think you could also use this data to do other tasks and think about it, because it's already connected to this DIDO pi bullet simulation task, for example. So yeah, so we're basically going to release all of this open source so that you can use it and play around with kind of the methods that you have, or even define new tasks as well. And then we also proposed this TOM-GNN network that combines topological and geometric information to be more robust and basically better at part segmentation. So, oh, maybe one more thing that maybe leads also into the discussion that we could have, right? Like I posed this question of like, should we have an object-centric representation of objects, or should we just take RGB images as input? And I don't think this provided the answer. This is more like, okay, let's do it object-centric for a very semantic task, and let's see where we get there, right? And I think this still hasn't answered the question, but I would love to hear your thoughts as well on what you think is the right way to go about deformable object manipulation that is maybe not just pick and place, but actually goes beyond that. So thank you very much for your attention. And these are all my amazing group members and students and all the funding agencies, basically. Thank you.
I think for a question, there's a microphone there if you want to go to the microphone. Yeah.
Yeah. Thank you very much for the presentation, Jeannette. Very nice. So I have actually two questions. So the first one is for the TOM-GNN. Why do you use the point clouds and not the graph representation? I think this would be more efficient, right?
Yeah, we actually do use the point cloud as well. Sorry, this wasn't probably clear.
I'm asking, why do you use the point cloud and not only the graph?
Okay. Because, yeah, so we tried it actually just with the graph, but we do still need, it turns out we do still need some of the Euclidean and geometrical information to do this part segmentation, actually. So that still helps. If you only use topology, at least in the way we did it, we didn't find that this was sufficient to get like a state of the art basically on this data set.
Yeah, I'm thinking actually because in action recognition, if you model objects and hands as graphs and use these sequential or consecutive graph-based representations of the scene, you can, and graph neural network, you can achieve very good results. This is what we did. And for me, it's the same problem actually. I mean, it's a kind of action recognition problem for the different configurations of the tool. No?
Yeah, is this with Noemi, the work on the
this is independent actually.
Okay.
It's on action recognition.
Okay, it's completely different. But yeah, I mean, I don't know exactly what you've done in this, but one hypothesis of why it works well in your case is that you probably have like a full body of a person, and you're trying to do action recognition maybe in these local manipulation tasks. Is that right? So I would say one hypothesis is that there's still way less deformation And therefore, maybe it's easier to learn it just based on the graph. Is it still spatially embedded, so you still have the 3D information? Yeah, so this could be one reason, but I don't know. It's a good question. Yeah.
May I ask a second one? So I'm wondering actually whether information about symmetry would help in the last part.
Yeah, we haven't looked into this, but yeah, maybe this could be. So actually, symmetries. We did use symmetries in this work. The one here with the bed making, right, like where a person gets actually tucked in. So there we embedded equivariance in our policy architecture, so that no matter how the point cloud is like positioned, rotated, or uniformly scaled, the robots still do the same policy, basically. So, and this is basically one version of symmetry that we use there. So that was really useful to embed it there, but we haven't, connected these two dots or two works. Yeah. Yeah.
Last question. Hey, so you've got the clustering step.
Yeah.
The very first one. Is that that's not a gradient? That doesn't have gradients through, does it?
Huh.
Yeah, it's definitely doing
This clustering?
Yeah. I mean, it's only a problem if you're using when you put through into this step. I was just wondering.
Yeah. Huh. That is a good question. I do think it should let gradients through. I don't know how. I don't know the details right now. Yeah.
I mean, if it's the first part of the network, it shouldn't matter.
Yeah. Actually, I'm wondering if there are even gradients pushed through this whole thing, right? Like, I think what is done is that you extract still features from the point cloud, but then completely independently you extract this graph structure, and then you use the graph structure, which is not learned, right? Like this, basically the filtering function, right? Like the filtering function and the cubes and the hyperparameters of that, they're all fixed, right? Like this is something we pick. And therefore, I don't think this needs to be differentiable. We are not back propagating through this step. Yeah.
All right,
Okay.
thanks, speakers.
Thank you.